We introduce the Sperner lemma since it plays a crucial role when studying fixed points, and many solution concepts in game theory are fixed points. The Sperner lemma is also important when studying computational complexity of fixed points and algorithms to find them. Start from a simplex. In the case reported in the picture, we have a two-dimensional simplex, and therefore we have three vertices. Recall that the dimension of a simplex is equal to the number of vertices minus 1. Given a simplex, we are interested in dividing the simplex in a number of sub-simplices, as in the figure. A simplicial subdivision does not need that all the subsimplices are regular as in the picture. They can be different, for instance with different sizes and forms. Given a division in subsimplices, we are interested in labeling the vertices of the subsimplices. In particular, we are interested in a specific labeling called Sperners, in which the labels belong to a set of n plus 1 different colors, or generic labels, where n is the number of dimensions of the simplex. So in the picture we have three vertices, and therefore we need three colors. We use blue, green and red. The first constraint in the Sperner's labeling is that each vertex of the simplex must have a different color. So in the picture, one vertex is in red, another in blue, and the third in green. The second constraint in the Sperner labeling is that each vertex of a subsimplex that is on a facet of the simplex must have a label of a vertex of the facet. Consider the facet in orange. The vertices of the simplex belonging to this facet has the red and blue colors. So all the vertices of the subsimplices on this facet can be colored only in red or in blue. Consider the facet in orange. The vertices of the simplex belonging to the facet have the red and green colors. So all the vertices of the subsimplices on this facet can be colored only in red or in green. Finally, consider the facet in orange. The vertices of the simplex belonging to this facet have the blue and green colors. So all the vertices of the subsimplices on this facet can be colored only in blue or in green. The third constraint in the Sperner labeling is that each vertex of a subsimplex that is in the interior of the simplex can have any label. In this case, such a vertex can be colored in red, blue or green. We need to introduce some definitions. We call a subsimplex panchromatic if all the vertices of the subsimplex have different colors. Since by definition a subsimplex has a number of vertices equal to the simplex, a panchromatic subsimplex has all the labels. Here an example of panchromatic subsimplex marked in orange. Here another example. We call a subsimplex quasi-panchromatic if all the vertices of the subsimplex have different colors except one. Again, since by definition a subsimplex has a number of vertices equal to the simplex, a panchromatic subsimplex has all the labels except one. Here an example of quasi-panchromatic subsimplex marked in orange, in which the green label is absent. Here instead an example in which the red label is absent. Now the statement of the Sperner lemma. It states that there is always an odd number of panchromatic subsimplices, and therefore that there is always at least one panchromatic subsimplex. This existing result plays a crucial role when, for instance, proving that the Nash equilibrium or the market equilibrium of Harrow-Debreu exist. Sperner also provides another interesting result that is important for characterizing the complexity of fixed points. A walk is defined as a sequence of adjacent subsimplices. Here an example of walk. Among all the possible walks, we are interested in walks called Sperners, such that all the faces traversed by the walk when moving from a subsimplex to an adjacent one have the same set of hand labels. Suppose that we focus on faces with red and blue colors. So the remaining color is the green. This means that for a Sperner walk, we need to consider subsimplices in which two vertices are colored in red and blue, and the remaining vertex can be any color. For instance, we start from a subsimplex that has the red and blue colors, and we move to adjacent subsimplices traversing red-blue faces. Here the first step of the walk, here the second, here the third, and so on. Notice that we cannot move from the last subsimplex to another subsimplex. Indeed, if we traverse a red-blue facet, we leave the simplex, as it happens in the picture. Furthermore, consider the first subsimplex of the walk. If from no other subsimplex we can move to it, we say that the walk starts from outside the simplex and enters the simplex, as it happens in the picture. Importantly, all the subsimplices traversed by Sperner walks are either quasi-panchromatic or panchromatic. This easily follows from the fact that subsimplices have at least n labels. So, if the vertex not belonging to the traversed facet has a label different from the labels of the facet, then the subsimplex is panchromatic. Otherwise, it is quasi-panchromatic. In this case, all the subsimplices are quasi-panchromatic. In this case, instead, we start from a quasi-panchromatic subsimplex. We traverse red-blue facet until we reach a panchromatic subsimplex. Consider panchromatic subsimplex. Given hand labels, there is only one facet with that set of labels. In the picture, only one facet has, for instance, the colors red and blue. This means that a panchromatic subsimplex can be either the starting point or the terminal point of a walk. Given a quasi-panchromatic subsimplex, we have only two faces with hand labels or colors. This is because we have n plus 1 vertices such that n minus 1 vertices have different labels, while two vertices have the same label that is different from the labels of the previous other n minus 1 vertices. So, to have n labels, we need the n minus 1 vertices with different labels and one of the two vertices with the same label. This means that fixed a direction once the walk enters a quasi-panchromatic subsimplex, there is only one way to leave it. Notice that this shows that a walk cannot terminate in a quasi-panchromatic subsimplex, since once a walk enters a subsimplex, there is always one way to leave it. Using this argument, we can show that the walk cannot enter loops. Assume that we have a loop, as in the picture. In order to have a loop, we need that a subsimplex has three faces with hand labels, in such a way that the walk enters the subsimplex, leave it, and then re-enters from a third facet of the subsimplex. But as discussed before, every quasi-panchromatic subsimplex has only two facets with n given labels. So Sperner loops is not possible. Now our goal is to characterize the maximal Sperner's works, that is, the works that cannot be further enlarged. We can show that they can be of four classes. Here the first class. Suppose that the Sperner's work enters the simplex from outside, traversing a facet of the simplex. In the example, the facet in violet. We can show that if the Sperner's work leaves the simplex, then it must leave the simplex from the same facet from which it enters. To avoid confusions, the subsimplex in which the work enters the simplex is different from the subsimplex from which it leaves the simplex, but the facet of the simplex is the same. Consider the example in the picture where the work enters traversing a red-blue facet. If we look at the other facets of the simplex, their colors cannot be, by definition of Sperner labeling, red and blue. They can be only red-green and green-blue. So in this case, the work enters and leaves from the same facet of the simplex. The proof is easy. At each step, the Sperner's work traverses only facet of subsimplices with a fixed set of n labels. If we focus on the facet of the simplex, these facets of the subsimplices are present only on the facet from which the work entered. In the facet in violet, we have not the blue color, so no red-blue work can leave the simplex traversing this facet. In the facet in violet, we have not the red color, so no red-blue work can leave the simplex traversing this facet. Now a simple observation. Obviously, the same work can be traversed along the inverse direction. Here the second class. Consider again a Sperner works entering the simplex. If the work does not leave the simplex, then it must reach a panchromatic subsimplex. Here an example. We need to prove that if a work enters the simplex and does not leave it, then it terminates in a panchromatic subsimplex. We already know that a work cannot enter a loop and that the work can terminate only in a panchromatic subsimplex. Since the number of subsimplices is finite, if the work does not leave the simplex, it must terminate in a subsimplex, and this must be panchromatic. Here the third class. Consider the case in which a Sperner work starts from a panchromatic subsimplex. We already know that a work can leave the simplex, but if it does not leave the simplex, it must reach another, different panchromatic subsimplex. Here the example. It is trivial that the work cannot re-enter the same subsimplex from which it started. It follows from the fact that the panchromatic subsimplex has only one facet with a given set of n labels. As well, we already know that a Sperner work cannot enter in loops. So, since the subsimplices are finite, the work must terminate, and it can terminate only in another panchromatic subsimplex. Finally, the fourth class. We can have cycles over a sequence of only quasi-panchromatic subsimplices. Here an example.